asked me to give one of the plenaries when he started in 2018, and my talk was carbon nanotube fibers turn 18, which is what had happened at the time. And I thought, you turn 18 and you're ready to go. But in these days, you really have to go to college, right? And then how long are you going to be in college? That's why the title is like this. So let me start, actually, this is essentially the same slide that I used to start in Madrid, right? So discovery of nanotubes in 91. By the mid-90s, it's clear that carbon nanotubes are a class of materials. And people start talking about applications, and they start talking about strength in the tens of gigapascal, perhaps even 100 gigapascal, so 100 times stronger than steel, twice the electrical conductivity of copper, 10 times the thermal conductivity of aluminum, and so on and so forth. But another thing happens in the mid-90s, that Rick Smalley attains what by that time would be considered a large-scale production of pretty good nanotubes. At that time it was laser oven and then became HIPCO, and sets up a non-profit so that people can just order the material on the rise and start trying out applications. And what turns out in application developments is really hard. So by the year 2000, which is where Scientific American published this article, very few application articles were being published. There was a lot of fundamental physics, really. And it turned out that making macro-scale materials is very difficult. So Scientific American in December of 2000 writes this rating of applications for carbon nanotubes. And one of them is super strong materials. And here is the image of carbon nanotube stress test, and they rate it as a science fiction, right? So this is December of 2020. By complete accident, I used to get Scientific American before Science. So I got this actually in the middle of November 2020. And that morning I go to Rice, after I read Scientific American at home, and this paper is in the issue of Science, which is actually November of 2000. And Philippe Poulain and his team in Bordeaux had already made these macroscopic materials. So first of all, it tells you that how bad are people at predicting what's going to happen. So Scientific American had just rated this science fiction, and they didn't realize it was already published in Science that week. What was very interesting also about this article is there was a lot of science. It wasn't just a shake and bake. Philippe had really understood how to control carbon nanotube dispersions by using surfactants, and had shown that if you have not enough surfactant, then you end up with undispersed material, which is this type of morphology. If you have too much surfactant, you have depletion, and this was all explained yesterday in one of the talks. But if you have just the right amount, you can get a high enough concentration that you can make fibers. And it looked like a scalable process, right? You load up a syringe and you go. So you could make this gigantic syringe or a battery of syringes, and you never had to stop. So that was very exciting. And Ray Baldwin and his group followed up with a variation on the theme after a couple of years. And then nothing happened for a couple of years, or it looked like nothing was happening, and there was a great vintage of 2004, where essentially all the methods that we know now for making carbon nanotube fibers were published. I don't think there's really anything that has taken on a large scale that's outside either the Poulain variations of the Poulain method or variations of this method. So Alan Windle was the first to publish the direct spinning by pulling the material directly out of the reactor. Our group with Rick Smalley was still alive at the time, did the spinning from liquid crystalline solutions in acids, and Ray Baldwin did the spinning from arrays. One thing that's very interesting, if you go back at these papers and you parse through the properties, they're not that different, right? The strength is within a factor of 2, really, and the conductivity, it's a little bit more broad, but now we know that these were doped, right? And there was some residual acid. The Cambridge material was really difficult to measure the density at the time, so maybe this was the right number, maybe it was not quite the right number, but again, within an order of magnitude, right? And certainly not even within an order of magnitude of what I had in my first slide, right? So very, very far from these ideal problems. So it was a bit of a bummer. And then, people thought that they should abandon this in the late 2000s. But then something else happened, is in 2013, we didn't even think ourselves that we could publish a paper on carbon nanotube fibers in Science again. But it turned out that we did enough that this paper was published. And what we show in this paper is we got multiple functionality, or multifunctionality. So here you have a couple of Ashby plots. One is strength versus electrical conductivity. Another one is thermal conductivity versus electrical conductivity. These are specific, so normalized by density. But so you see that in both cases, the fiber has multiple functionalities. In the ballpark of carbon fibers and other carbon nanotubes fibers for strength, in the ballpark of conductivity for metals, higher thermal conductivity, and so on. And the other thing is, this actually was done with Teijin, which used to be the old AkzoNobel, which was a company that scaled up Tvaron, which essentially was a European variant of Kevlar. And so we said this is a scalable process. We were spinning out on a spinneret, and now 37 spinneret making big rolls. And so multifunctionality and scalability was proven already 10 years ago, right? Okay, we'll see. So then I got to talk about a little bit of science, and there's a bunch of young people who weren't born when this stuff was done. So how was this done, right? So you got to go from a carbon nanotube fiber. So this is over here we say we're using bulk grown nanotubes. So these are not order. So you start with bulk grown nanotubes. You have no structural integrity, no ordering, and you got to make something that has structural integrity and order. How do you do that? Well, if you can use a fluid phase, you have a lot of advantages because it's scalable, but you also can use a technology platform that was already used for other materials like Kevlar, spectral dynamium, PBO, and pan-based carbon fibers, right? So what would you expect if you do that? Well, you expect something like this, that if you can get the nanotubes to get into a liquid, you would expect that they would behave roughly as rods. And so when they're dilute, they should act individually, and then progressively they should find themselves until at some point they would get so crowded that they could not exist in a disordered state in the liquid phase. And so they either would phase or crash out a solution, or they would phase separate into a liquid crystal. And what's very important, this is already known for a century, is that when this type of liquid crystallines appear, there is a region of phase space, or a range of concentrations, where these two phases are in equilibrium with each other. So you have an isotropic phase and a liquid crystalline phase in equilibrium, and then you can go to higher concentration. So we set out to see whether it was working. Now, this is before the 2013 paper, right, to get the basic science. And indeed, if you look at individualized carbon nanotubes in water, you see they behave a lot like rods. In fact, you can use the equations for rods and confined rods to actually model their diffusivity. You also notice that the longer ones actually fluctuate a little bit in shape. And if you go look for really long ones, so this is about 15 micron, you do see these shape fluctuations. And so you realize that, of course, like any material, they have a finite thickness. This is actually published in PNAS a long time ago, so I think the movies are online if you guys like them. So you can actually treat them as a semi-extensible and extensible, semi-flexible and extensible Bryner rods, and you can actually measure the bending stiffness by looking at the persistence length, which is the ratio of the bending stiffness to KT, which is your thermal energy. And you can measure the persistence length by looking at the correlation length of a tangent along the contour length, right? And the cool trick about this was also like, of course, you expect this to depend on the diameter of the nanotubes, but the microscopy image does not give you the diameter. And so we worked with Bruce Wiseman, who had developed a way to take the spectrum of an individual nanotube in a fluorescence microscope. And so we would take the spectrum and the images essentially at the same time. We just switch the beam to the spectrometer, get the spectrum, switch it back and get the images. And then by doing image analysis, we could get the amplitude of the bending modes, and from that, the persistence length. So the persistence length, it turns out, for the single wall nanotubes is in the 20 to 150 microns, and it scales with the diameter cube, which is exactly what you expect for an empty pipe. So that leads you to then say, how do you process? Now, you can't process in surfactant, or you can, but then you got more surfactant than nanotubes. So if you can use a pure liquid, it's better. And we used acids, because acids were known to protonate stiff polymers. And in fact, they've been used for Kevlar and PDO. And so it turns out that if you take right nanotubes, put them in an acid, chlorosulfonic acid works better because it's stronger. You can use other acids. You can see the formation of liquid crystals. That's the same image in transmitted light, where you see just a little bit of non-uniform concentration. But then in polarized light, you see domains that turn on and off, and those are your liquid crystals. And then you can use a liquid crystal in ordering to control the liquid, and then spin out of a spinneret. That's a spinneret over here has only one hole. And spin into a coagulant, remove the acid, and pick up the fiber. And you get naturally this very well aligned fiber because the nanotubes are already aligned in the liquid. You can also make foams by injection molding, and you can make films or coating, and then you can see that this is scalable, right? So this is now with multi-filament spinneret. So that's up where we were in 2013. Then we went on and say, okay, but these properties, we got multifunctionality, but as Mia Ciocci used to say, it was an excuse for saying that none of the properties were very good, right? So we said, how do we get the properties to be better? And how do we understand the phase behavior of these materials? And we started working with carbon nanotubes from many different manufacturers. These are carbon nanotubes that we didn't make. They were coming from about 19 different labs, some of them university labs, some of them commercial. And what we saw is that, again, as expected by classical theories, this transition from isotropic to liquid crystal happens as you increase concentration or as you increase length, and the two are related with this type of behavior. So as we had at the beginning is the transition goes as the inverse of the aspect ratio, where the aspect ratio is length to diameter. So here you see shorter tubes, these are HIPCO, longer tubes, these were from Samsung when Samsung J was still making nanotubes. And as you go up in aspect ratio, your transition from isotropic to liquid crystal happens at lower and lower concentration. It turns out that when you're at a low concentration, you can actually measure length by looking at the viscosity of a droplet of carbon nanotube solution that's being stretched. You can back out the viscosity from this method, and from the viscosity you can get the length. So you can get the length two ways, one by viscosity, another one by using the transition to liquid crystal. The distance between this line, which is the theoretical Onzaga line, and this line is due to polydispersity of the samples. So now that we knew how to measure length, we could make fibers with these materials, and we saw that in addition to crystallinity, which you measure by looking at the Raman G to D ratio, there was another property that was important, which is the aspect ratio of the nanotubes. And roughly, the tensile strength and the electrical conductivity scale, let's say, roughly linear with the length of the nanotubes. This is not surprising. This is what you would have expected based on polymer processing, polymer properties laws. Now, you can look at this a little bit differently. You can look at this, how did we do versus time? And I started putting down this stuff only recently. And the reason I put only stuff from our lab is because this one I can swear by. It's every one of these points was measured at least in two labs. Even at the beginning, everything was measured both by Jack Fisher at Penn and by Asa Rice. And so we see that both the strength and the electrical conductivity essentially doubled every 3 years. Partly because of better processing, partly because of longer nanotubes becoming available via collaborations. So we started a company under funding from the Air Force in 2015. It's called DexMat, Deus Ex Materia. Of course, I have a conflict of interest, and these are some of the samples, and if you want to play with them, I have them here. So by 2021, this thing of multiple functionality was looking better and better. So that's the 2013 points. You see that now the points went up quite a bit. There were also other papers on carbon nanotube fibers that reported better properties, and plus the fibers inherited a lot of the good properties of carbon nanotubes, like low density, corrosion resistance, and some that were emerging properties like high flexibility that wasn't really expected at the beginning, or high fatigue resistance. And we started seeing more and more papers in the literature from groups that were not making fibers. For example, this is by Mia Sioci, working with material made, at that time it was still nanocomp, now it's Huntsman. And it was interesting to see that even at the application side, at this point, people started seeing emerging properties. For example, here, this is verbatim from the conclusions of the papers, you can read them yourself. But what Mia observed is that even though this yarn was not as strong as the IM7 hexyl fiber to which it was being compared, once it was made into a composite tank, it had analogous performance. This is from my group where we looked at wearable electrodes. So there was another thing that was not quite expected. When you put these fibers in contact with the skin, they make very good electrochemical contact, and so you can get the heart rate, or you can actually get a medical quality EKG, and you can solve these fibers onto tissues, which again is something that nanocomp had seen at about the same time. Other things that were unexpected is high-speed impact. So this is a paper by Jae-Wang Lee at UMass. We collaborated, but we really just provided the fibers for this paper and helped a little bit with the interpretation. So what you see is that it took aluminum manual Kevlar and nanotube fibers. And in this case, the nanotube fiber was significantly weaker than Kevlar. And however, upon high impact, they behave better. And it was very interesting is when we got the result, I told Jae-Wang, send us back the fiber, we'll do Raman. And we did Raman at the end of impact. At the point of impact, we saw a lot of SP2 to SP3 transitions. So the D band was much higher, which meant that when the bullet hit, actually we broke covalent bonds, right? Or bullet covalent. So that's actually something that was not expected. This is another one. These are people who saw DexMat videos where they throw axes at the nanotube fibers, and the axe can knock out the nanotube fiber. So this group bought some of the fiber. It's Wenon Chen from Purdue, and looked at the blade cutting and saw that the CNT fiber had significant better blade cutting resistance than Clever, the NEMA glass. Ceramic is a silicon carbide fiber. Other work, this is out of Jonghyun Park here in South Korea. This is a group that has power electronics, and they saw that the carbon nanotube fibers were behaving better than copper, higher efficiency in a situation where you want to do wireless charging, wireless power transfer. Or another situation where they looked at proximity effects. So proximity effects is when you have two wires that are almost parallel, and the AC current in one wire generates a magnetic field that interferes with the neighboring wire, and they saw significantly lower proximity effect in nanotube fibers compared to metals. And it was not due to conductivity, because they took lead, which had about the same conductivity as carbon nanotube fibers, and they saw a different behavior. So it's very encouraging when you see people that you don't even ever talk to that publish papers with the material, right? And so, you know, can Benji come up with a truck and back it up and fill it with carbon nanotube? Yeah, right? So what are we then? And the answer is, you know, we're not there, right? So this is data from 2021. And what it shows is the capacity for multi-wall carbon nanotubes, which are really useless for fibers. You know, I know I'm not being very polite, but that's what I think. So the capacity is pretty high. You know, we're talking about in the 8 total kilotons a year, and it grew significantly. We had a talk yesterday from LG Chem. LG Chem more like tripled the capacity already last year. Now, for the single wall, you see that the capacity was about 80 tons a year, and that was all occupancy. So it's about 1%, and the growth has been very slow, right? So since 2021, there's been no growth on capacity to speak of in this side. It's hard to estimate the fiber capacity. So if you guys want tonight at the banquet, we do a table with everybody who does fibers, gets drunk, and we basically put down the numbers. And then we see, you guys can, and then everybody else can do the over-under. My estimate is a ton a year capacity, okay? And I see that David Kelly's just shook his head saying yes, so that is very encouraging. And I was backing up Sinano, it looks like they're about 500 kilos a year for sheets, and fibers usually a little lower. One thing that also would be interesting to see, what's the utilization factor? So not so much what's the capacity, but how much of that capacity is actually being sold. Because that's a very important number, and it's almost impossible to get it. These are capacity, they're not sold. The other thing that's kind of unfortunate is most of the stuff is going to batteries and polymer composites. And the frustrating thing is that these are applications that use a low volume fraction of carbon nanotubes, and therefore have a higher added value. Right? If you're displacing carbon black at 1,000 to 1 ratio, you can command $1,000 a kilo or more for your material. It's hard to sell fibers at that price. So the fiber capacity is 1% of the fiber grade, if my guess or my estimate is correct. And it's 10 to the minus 4 of the total capacity, right? And then we had these other things, which are, of course, tragic by themselves. But, of course, you guys know where this capacity was, right? It's in Novosibirsk, right? So all of a sudden, when this happened, which nobody, including Oxial, even thought it was possible, it put us into this really tough geopolitical situation, which was actually good for a lot of the other battery material manufacturers, because Oxial was taking a very strong hold on that. So now, you know, these are some of the things that we've been dealing with in the last few years. Now, the other thing is from that same Bloomberg report, this is what the Bloomberg report says. And if you never wrote anything like this in a paper or never said it in a talk, you're golden. But I have said these things, okay? They're not even wrong. They are just inappropriate. So, you know, I have a degree, I have degrees in chemistry, I have a PhD with a minor in theoretical mechanics. I reflected a little bit on this. When does a concept of strength, electrical, thermal conductivity come up? They come up in the early 1800s with the theory, continuous theory of fields. You know, this is Cauchy that we talk about when we do calculus, because it did infinitesimal quantities and essentially says matter is continuous and you can divide it infinitesimally as much as you want. And therefore, these are properties that are defined for continuous media, right? And so you have to have something that is large enough and homogeneous enough compared to a molecule that you can define this. And you know, James and Milo, if you disagree, just bring it up. But you know, I was referring a paper and I was arguing with this, and somebody, one of the authors, brings up a paper by I can't remember. So you know, a paper from the late 90s. And I'm like, Cauchy wrote this stuff 200 years before. Okay, listen to Cauchy, listen to Fourier. And so we need to stop saying these things, right? These are attributes of continuous media, and we cannot talk about individual molecular particles with those attributes because we confuse people. The other thing is we don't have name differentiation. We keep talking about carbon nanotubes, and we say it's a material class, but we don't know how to call the members of the class other than saying multi-wall, few wall, single wall. But then single wall, you can have stuff that we thought it was great, like HIPCO, and it's actually was marginal for fibers, and you can have stuff that is really great for fibers, and a number of people in here are making. And for multi-wall, you also have a lot of differentiations. So we don't know how to call, we don't really have names for this, and we need to somehow come up with it. I don't have the names, otherwise we'll tell you what they should be called. And this is generating confusion. Now, some customers are more sophisticated. So the people who are not getting confused very much are the people who are just a step downstream from the carbon nanotube manufacturers. Those same people 20 years ago, they were getting very confused. They learned, and now they know how to assess the material that they're receiving. But there continues to be confusion in funding agencies. Investors have massive confusion, and the general public, and also as you go downstream in supply chains farther away from integrators. And this is a recipe for having another hype cycle, which I know Benjamin's not worried about because he's right with the truck, but I am worried about, and I think Dave is worried about too, because we're right there trying to get this to work. Why the heck this happened? I just told you that 10 years ago, multifunctionality and scalability was proven, right? Come on, it's public science, must be right. So how did we prove scalability? And this is really done bona fide with 5 people from Page, right? And this is in the supplementary. And if you want to amuse yourself and laugh at me, read the supplementary. This is actually true, right? There is a power law. As you make something bigger, the cost that goes with the volume to a power n. If you duplicate, n is equal to 1. Now, normally, engineers are better than that, and they can get a power that can be as low as about 0.66. That's usually the best you can do, right? And so we thought, okay, we now slotted it into the paradigm for making aramid fibers, and we knew that for aramid fibers, the power law is about 0.7. Therefore, this is scalable. We won't have to duplicate instruments. And the law, however, is this. The cost of a fiber per kilo, it's the cost of the nanotubes per kilo. You can't make the fiber cheaper than the nanotubes. Plus the cost of the processing material that you need. For example, you may need solvents, you may need coagulants, you may need energy. Plus, this is the part that has what's called the capital expenditures or operating expenditures. So that's the one that scales. These don't scale. You need a kilo of nanotubes to make a kilo of fiber. You can't get anything better than that. So why is it that we messed up, right? So we were wrong, and the reason why we were wrong is that we didn't calculate this prefactor and these 2 numbers. This number we knew that we didn't have a lot of control, but see, you say the cost of high quality CNT is relatively high, but it's coming down. These were made by CC&I, that as we were writing the paper got sued by Unidyne to a standstill, and the 2 companies collapsed soon afterwards. So much for that part of the scale up. This, we had winged it, okay? We hadn't really looked at the cost of chlorosulfonic acid, organics, et cetera, that needed. And the other thing is the prefactor matters, right? You can have something that scales with a good scaling law, but if you have a high prefactor, it's going to take a long time before you catch up with something else. And the reason why this was much harder than expected is because we were spinning a low line speed and low synthetic concentration session. So that's pretty pure utilization of your spinning setups. Okay, so we were wrong, okay, but the multifunctionality was right. Okay, so at least we got half of the paper right, and that was the thing that was more surprising. So now I got to explain to you what is contrapasso that I talk about in the abstract. So we got indoctrinated with this when we were in high school in Italy. Dante Alighieri wrote this Divine Comedy about 700 years ago, and it's divided in 3 books, and it talks about him going through Hell, first book, Purgatory, second book, and Heaven, the third book. The fun one is Hell. And when he goes through Hell, he meets people, many of them were public figures or people he knew personally, who are now in Hell, and they're receiving punishment for things that they had done during life. Some of these people were still alive, and he just projected that they would be dead, right? And contrapasso is the just punishment for a sin that is affected by either something that resembles your sin or something that is contrasting with your sin. For example, if you really like to eat, a type of contrapasso would be you would be forced to eat continuously until you burst. On another one, you will continuously shown food that you really like but never be allowed to touch it, right? So this would be a type of contrapasso. Dante was much more sophisticated. So I think that's what's happening to us, and maybe this is because of the sins that we've done during the first life cycle. And the problem that we're facing is this right now, right? So so I'm switching to climate now, right? Is we have a CO2 concentration in the last million years, and it stays in a certain band, and then the Industrial Revolution starts. This is not the fault of carbon nanotubes, right? But it's the Industrial Revolution, and all of a sudden this goes up, and it's getting hotter, and so you start getting more and more news that basically are telling us that life on Earth is going to be like hell, right? And then they tell you we must decarbonize. So first of all, we can't decarbonize. We are made out of carbon. Half of our body is carbon, half of our food is carbon, half of our clothes are carbon, 100% of our publications are carbon, so we can't decarbonize. So you can even buy t-shirts and that says you're carbonized. So we also have a problem on language, not only in carbon nanotubes, but also in how we call carbon dioxide. We use the same word for carbon dioxide. So this I made a word, and I think we should just call it COX and use this word, which makes it sound like detox, like when you're addicted to something, or addicted to burn. But there's a lot of solutions to this, right? People tell you, we have all these solutions. We can do CO2 capture, we can decarbonize steel and aluminum, we can use hydrogen, we got renewables, we can lightweight everything, electrify everything, etc., etc. Well, guess what? They're contrasting drivers. Let me give you an example. You want to lightweight, you have to use aluminum or carbon fibers in place of steel. It takes a lot more energy, and there's a lot more CO2 emissions in making aluminum or carbon fibers than in making steel. You want to electrify, you need to move the electricity, you need copper or aluminum. And again, it's a lot of CO2 emissions, and an electric vehicle is significantly heavier than internal combustion vehicle. Especially when you electrify a plane, that's going to be a hard one. Renewables takes a lot of materials and a lot of resources to build a wind farm or a solar farm, much more so than to build, let's say, a power plant running on natural gas. Hydrogen. All hydrogen on Earth is bound to oxygen or carbon. So if it's bound to oxygen, we're running a cycle because we're going to use the hydrogen by essentially recombining with oxygen to get energy. If we want to get it out of carbon, then we have to deal with carbon. Normally we produce CO2. And you see how this goes, right? And so it's a little bit like fighting a hydra, or for those of you who used to have Boris Johnson as prime minister, playing a game of whack-a-mole. And so you're gonna just whack it completely. I know. I used to use whack-a-mole before Boris Johnson used it, so now I use the hydra. I know. We got Trump at the same time, so it's okay. it's okay. Democracy is, survive this. But if you use carbon material, and this is a carbon shot that we'll talk about, I think you can solve all these at once. And let me look at a couple of things. One is, what's the problem with hydrocarbons? The problem with hydrocarbons is not so much extraction. There's very little CO2 emitted in the extraction of oil and gas. And even natural gas has very little methane emitted if you do it properly. If you look at Norway, because Norway uses electricity and heavily fines emissions of methane, you end up having, you could have methane from Norway, for example, with very low CO2 footprint. The problem is all downstream. At some point we combine with oxygen, we meet CO2, because CO2 is about 70% oxygen, 30% carbon. There's a small stream over here, which is polymer, lubricants, and chemicals that don't have stoichiometric CO2 emissions. Now, we want to get rid of this, but it's hard because this is how much of our energy comes from burning, right? But let me look at this a little more. This is mostly carbon in mass, right? A little bit of hydrogen. But if you look at the energy, half of the energy is in the hydrogen. There is a delta H of formation for hydrocarbons from carbon, but it's small. It's about 10% of the total. So if you don't think about that, you can think about hydrogen having half of the energy. So is there a way to use carbon as a material and the hydrogen as energy? In this case, half of this energy would be available. Now, if we were to use carbon material, but this has to be on a large scale. These are gigatons, okay? They're not kilos or kilotons, they're gigatons, billions of tons. Where do we use a lot of materials? So this is also from Ashley. It's an Ashley plot by Ashley. And it shows, how do we use materials. So carbon black is the most used carbon material, and you see it's very small compared to polymers, metals, ceramics, and natural material. Carbon fibers is a couple of orders of magnitude smaller. Right now it's a little higher, but it's still about 100,000 tons a year. So the first thing that you see is structural integrity is key for widespread use. You cannot take a powder and go to large scale. Carbon black is not used at larger scale because it's a powder. By the way, there is a version of it talk on the web. I see a lot of people are taking pictures, so I feel very good about it. So you don't have to bootleg it. There is one on the web. You could go after, you don't want to go after natural materials. So your wood is great. The wood blocks CO2 into a solid, and so you don't want to change it. Over here, ceramics are a hard sell. It's very low value, 5 cents a kilo. So you may be able to do something if you can reduce the amount of ceramics that are being needed, but to outright displace ceramic, it's hard. But over here, there's much lower hanging fruit, whereas metals. And it's because the values are higher. You start at about $1 a kilo for steel, then $7 a kilo for copper, and then as you go down here, you get higher and higher. And these are at the low end, right? This is bulk steel, bulk copper. If you go, stainless steel is about an order higher. Wires are even higher. Now the other thing is, this is more of the heart to the carbonized industry. The emissions from steel and aluminum are the highest. Here I use 720 tons for aluminum a year. It actually, recently I saw it's more closer to 1.1 billion tons to make aluminum. There's another thing, which is, right now we got climate tunnel vision and we're only looking at CO2. This is what's happening. Is that there's other problems in mining. This is bauxite mining and deforestation in Brazil to get aluminum. So these you can't really quantify with CO2 emissions. But isn't extraction of oil also bad? Of course it is. It's an extracting industry. Let me show you the comparison. This is about biggest copper mine in the world. It's called Mina Escondida. It's in Chile. It's actually on tribal land, and there's indigenous people being displaced. The mine is over here, the tailing pond is over here. It's about 1.1 million tons a year. This is Perdido, which is one of the largest oil platforms in the US and the Gulf of Mexico. It makes about 5.5 million carbon a year, or extracts 1 million ton a year of hydrogen. Any guess on how big this is? It's about half of a soccer field. So if you put it on the same scale, that's a platform, and that's a track shop of a mine. That's okay. So in terms of an extractive industry, oil and gas has a very, very low footprint if you do it properly. And the reason is copper, for example, is currently mined at 0.3% concentration. So you need to move a ton of copper to get 3 kilos of ore, and these are current mines. As you look at projected mines, these numbers go down. Then if you look at the energy we use, it's about 12% of the energy used. So if we could make carbon, if we could substitute these functions with carbon, we could actually save all this energy. But wait a minute, substitute this function with carbon, that's exactly the multifunctionality we were talking about a little bit ago, right? So we could already substitute these functionalities with carbon because we have overlapping properties. So when Bill Gates says, what's your plan for steel? We say replace it, make steel obsolete, and use the carbon to make everything. And so the pathway is something like this. And again, if you're interested, this is published in PNAS about 2 years ago. You start with hydrocarbons, could be natural gas, could be other volatile hydrocarbons. You know, we know how to make carbon nanotubes pretty much of any of these molecules and then more. Or it could be ethanol, right? It's just fine. You split it. This is for methane, so you get more hydrogen if you split methane. Some of the other hydrocarbons give you less methane. But it's key that this has to be a material that has the potential for structural integrity, so you can turn it into fibers, tapes, 3D structures. And you want this material to have properties that overlap at least with metals and perhaps even more broadly. And if you can do this, then you got a shot at displacing metals, and then you could put these materials into large scale supply chains and large scale volumes, right? And this could not be done until until 20 years ago. This would have been complete science fiction, as Scientific American was saying. You can't do this with carbon directly, but now you can. You can do it with carbon nanotubes. You may be able to do it with graphene. I'm very interested in hearing the progress on graphene fiber from the tomorrow's plenary. But properties is not enough, right? So what you have to do is something like the sunshot. So remember, some of you are old enough like me to have lived through a period where there was a lot of skepticism on solar power. People would say, it's never going to be cheap enough. We're not going to be able to have solar panels that are cheap enough that they'll displace coal, natural gas, nuclear, etc. Right? And those of you who are here in grad school, they never even heard it, because by about 2010, so probably some of you were not even in high school, the cost of solar panels dropped to below the cost of fossil fuels generated energy. And so they got to parity, and now solar is penetrating. So that's essentially what we'll have to do, is get this material, carbon nanotube fibers, to cost parity with carbon fibers, high-end steel, copper, aluminum, at some point even rebar steel. And that's hard. It's going to require to get the price of the nanotubes that go into the fiber below to $50 a kilo. At $50 a kilo, you can't displace this, but you can start displacing some of this stuff, right? And so that number is pretty daunting. I mean, people haven't talked too much about numbers, but $50 a kilo is daunting. But if you think about the feedstock is cheap. You know, natural gas is $150 a ton. It's 15 cents a kilo, right? So we got to be able to do this. And to do this, we really have to understand reactors. And these reactors were really black boxes until about half a decade ago. There was one company out of Cambridge that was selling a reactor called Black Magic at some point, and it was awesome because that's what it was, right? And in the papers up to about 2015, there's no attention to efficiency, and the reactor understanding is really low, right? But in about 2018, we started on a program with Shell and ARPA-E. Then, Huntsman also participated in the same program with ARPA-E, Cambridge, Politecnico di Milano, where we started talking about can we really understand these reactors, and can we do a fully integrated program so that we do it with the idea that the material will be usable on a large scale. And there's been a lot of really, really good progress in the last half a decade. I mean, Cambridge led the way. You saw the talks yesterday by Adam Boyes and James Elliott. They really have been illuminating these reactors at every stage. Is from catalyst formation to the composition of hydrocarbons to the mechanism by which this aerogel forms. And so this has been incredible to have this science come up and be available to everybody who's doing synthesis. David Galius has led the team at Nanocomp. This is one of the slides from about a year ago from the ARPA-E meeting, where it shows where the process was when they started and where it is now. And look at the hydrogen. They were running basically hydrogen through the reactor with a little bit of methane, and now it's very well balanced. These are volumetric flow rates, so by mass, mostly what's going through, of course, is methane. And also they increase the conversion. They are now operating at pressure, which also lowers the capital expenditure because it makes the reactors more compact. So essentially there was improvement of all the metrics, just a little bit of trade-off on CNT quality, but it's very clear that this can be clawed back if they want. Now, one of the papers that came out the last few years, it's really qualifies as miracle in my, in my classification of papers. It's the team of Sangmin came here at KIST, and there was a really despair on whether these CVD reactors that were making high quality nanotubes could ever be efficient. And what Sangmin and his team showed that by understanding the fluid mechanics and the transfer in the reactor, it changing the point where the feedstock and the catalyst will be introduced, they could get over an order of magnitude improvement in the productivity without giving up quality. Actually, the quality of the material was even better. And Sangmin can explain this to you better than I do, but it has to do with the temperature distribution and the recirculations in the reactor. So again, this has been amazing. Again, an example of illuminating the reactor and then using the understanding to actually affect the positive change in terms of process intensification. We've been working with Sangmin and also with Adam and his colleagues at Cambridge. Glenn Irvin is one of my colleagues. And now what we see is that with some small changes to Sangmin's methods, we've gone up even higher, and we're basically making about 100 grams an hour of very high quality nanotubes. So these are fiber grade. Now, to give you a perspective, this was HIPCO. So when I was a kid and Rick Smalley was alive, this was the state of the art, and you couldn't touch it. Smalley was ramming 500 standard liters a minute of gas into the reactor and was making barely a gram an hour of material. 70% was nanotubes, and we're pretty short. These new reactors with a deeper injection, they're running about 3 to 4 standard liters per minute of gas, and they're making over a gram an hour, and the material is much better. That's roughly a measure of the intensification, because most of the energy goes into heating up those gases, right? And this is just a scratch. These reactors still mostly running inert gas, right? So if we can do what David Gaines and his team has done, maybe we'll do it with them and get that inert gas lower, it's going to be very important. But on spinning, there's been big improvements. The Bong-Chul Koo and his team with Juan Villatella showed that you can take one-spot fibers and make them even better by cross-processing. By getting to high temperature, you can get the walls of the fibers to fuse, and you can get this material that has really high properties. My contribution to this paper was the spider plot. that's all. But I see a lot of people are using the spider plots now. So there's also other process improvements. I see some people are complaining about chlorosulfonic acid. Yes, you should complain about chlorosulfonic acid. You don't really have to use it. There's a way to get almost the same properties. We're using weaker acid. If you soak the nanotubes into a strong acid first and then dilute with a weaker acid. And so this was also published, actually those two papers were published back to back. This was my team, mostly the PhDs, Robert Hedrick, that showed that if you pre-soak the nanotubes in a strong acid like oleum, then you can get the liquid crystal even in a weaker acid, and then this becomes drop-in for doing things like screen printing, 3D printing. You can coat these on PET, etc. Now, the other thing is that we did is we redesigned wet spinning. So remember this? So that's what we do now with wet spinning. That's how fast that roll is going. What that means is that we change the process, and I can't talk too much about it, but this kappa is now 700 times lower. And this is like 500 times lower. So this has been now intensified, and without really dropping the properties. So again, we hadn't paid attention to it. We paid attention to it now. You can really take down the cost of wet spinning if you want to. This is where we need help. And we don't need help just because in the lab we can do this stuff now, but scale matters. You can't take costs down just by intensifying in the lab. And on this side, we know how to scale it. We can do this with Dexman, for example. But on this side, that's where we really need help. A couple of things is, one is carbon fibers. So these are carbon fibers. This is something actually Alan Windle said a long time ago, is this material has a much simpler production chain than carbon fibers, right? It could be 2-3 steps, only one big chemical reaction from natural gas to carbon fiber. When people say carbon fibers are made out of pan, I ask them, where is your mine of pan? Where do you get the pan? Pan comes from natural gas, and you have to run separation of propane, cracking of propane. You have to run Haber-Bosch to get pan. You need hydrogen, right? And ammonia. And so no wonder that pan is such a difficult material. Pan-based fiber is so inefficient. And then, of course, you have to get rid of all this nitrogen and hydrogen you put in the fiber. So I think that the reason why I believe that this material can be a low CO2 intensity and low energy material is because it's a very simple process chain. So, contrapasso. For the fibers, I think our contrapasso could be that we got into this thinking this is going to be the best fiber anybody would ever make, and we may end up having to make the cheapest fiber that anybody would ever make. Okay, it's the saving grace is that it's made of carbon, which is very plentifully available, not the properties. For climate, these guys are kilifying carbon as a cause of climate change. They use decarbonization of carbon economy, and it may very well be that if we can get this done, they get saved by carbon. Carbon takes them out of this hotspot, and so that's going to be their contrapasso. We're going to have to go through hell for this, but I mean, here you can see, we're not going to go through all these good things that you can, you get how it solves a lot of these problems. The last thing is going to scale fast. Somebody had an equivalent of this slide. It was a little bit newer. And people said, wow, this is really fast. This is how carbon fibers went to scale. Well, it starts a little bit earlier, and it starts 100 years earlier if you go to this. But is this fast? This is where Qualec discovers Kevlar. In '65, Union Carbide had already commercialized the first carbon fibers. By the way, they were $25,000 a kilo in today's money. In 1982, DuPont opened the first 20 kiloton plant. That's how fast this went. This has been horribly slow, right? And so you may ask, why were carbon fibers so slow and why was Kevlar so fast? This is a slide that I took out of my talk that I gave in Madrid. This is what they did with Kevlar. It was done in a single company that controlled the whole supply chain and was fully committed. There was no going back. After they had built the pilot plant, they realized their solvent for polymerization was carcinogenic. They didn't stop. They changed the solvent on the fly as they were sampling to customer and building the first scale commercial plant. So they went from discovery of the molecule to full-scale commercialization in 17 years. And they had a slew of application development people who were working with customers to make sure that there was pull for the material. This is really not possible. I mean, maybe somebody could do this in China. I don't see how this can be done in the current manufacturing economy. And can it happen? And it's hard also because you need to make design changes at the architectural level. This material is different. This is like if you look at a stone bridge and you come up with steel and you say, well, steel is going to be much better to make bridges. And you go to the arch bridge builder and the arch bridge builder says, well, my bridge is made so that the material is always in compression. What matters is compressive strength divided by the density. Steel is actually worse against stone on that problem. If you make an Ashby plot, this steel loses on this. And this guy had stone masons on site cutting the stones, which you cannot do if you have steel. So you have to come up with a different architecture. If you do a suspended bridge, it's totally different. You can't do it with stone, right? And so how do we make this happen now? And what we did is we created the Carbon Hub, which a few people have mentioned it yesterday, to try to create a field and accelerate it. So this is not just a field of carbon nanotubes. is the field of carbon nanotubes that can be made into macroscopic material that have structural integrity, and they can be made sustainably. This is what Seguro Nodo was talking about yesterday. You have to take that full LCA and make sure that this material is has a lower CO2 footprint than copper, aluminum, steel. And so the carbonite is organized around essentially this virtual supply chain, where we got companies and university labs working together trying to push this through. This is the current project map. So you see there are several of the speakers here, Sangmin Kim, Vilatera, Boyce, Benji Maruyama, etc. And it's open. So with that, I'd like to thank my students. Now, these three just graduated. These three are graduating, so I'm looking for postdocs. So if anybody's interested, please come talk to me. And these are the agencies and the companies that are funding the effort, and that's it. Will you join us? Thank you.